Have you brilliant students to work on your laptop?
Okay, good. So it's my pleasure to welcome Junfeng Yang, because Junfeng is a professor at Columbia, and he's joined to work with many brilliant students. So,
I love my students.
So let me just give you a context of this kind of work. Right? So there's been a lot of work in improving determinism in the last like 3, 4, 5 years or so. We also worked on it like static analysis, dynamic analysis, finding logs, all kinds of system in the architecture and systems community on determinizing programs. So you have a concurrent program and determinize it, and the premise of that is deterministic programs are less buggy. And he's going to tell us today why this is not so.
Thanks for the introduction, Martin. Good morning, everyone. So today I'll be talking about our recent work on making parallel programs more reliable. It's joint work with my awesome brilliant students, Ming Cui, Junye Wu, Yang Tang, and Gang Hu. And by the way, we're also looking for undergraduate interns, PhD students, postdocs. If you guys are interested, let me know. So a quick summary of my talk. So first of all, multi-threaded programs are getting more and more critical and pervasive. But despite a lot of advances to reliability tools, these multi-threaded programs remain hard to get right. And if you ask your colleagues or maybe your advisor, why multi-threading is so hard, a knee-jerk response you typically get is, they're non-deterministic, nondeterminism, which means if you run a multi-threaded program, because the threads run in parallel, the instructions can interleave in many different ways across different executions, right? So that you can see, for this particular input for the same program, across different executions, you see different behaviors. Sometimes the program computes correct results. Sometimes the programs that do not compute correct results, they may actually crash, right? So this is, non-determinism, and conventional wisdom has blamed this non-determinism for the difficulty in getting multi-threaded programs right? But actually, in this talk, I'm going to argue non-determinism is more or less a scapegoat. What really makes multi-threaded programs hard to get right is, the reason is actually rather quantitative. These programs have just too many schedules or interleavings, right? The schedules interleaving is the same thing. So I will also talk about an approach we created called stable multithreading or stable MT. So this technique, this approach shrinks the set of schedules, right? Make the set of schedules a program may run into really small so that we can easily make the schedules reliable, right? And also the technique has a low overhead. So this talk will cover work described in a set of papers, including an upcoming CECM paper, which Moshe invited us to submit. So let's look at some background and motivation. So, the number of cores for machines are increasing, right? So there's this hardware trend to use multi-core processors. How do we actually get the maximum performance out of the cores? Well, people write multi-threaded code, right? Code that can run in parallel on the cores. And also we have this user demand, continuously increasing computational demand. Today we have like cloud computing, mobile computing, big data. So all these massive computations actually call for efficiency in performance. So people actually are writing more and more multi-threaded programs to handle these computations, right? So these programs are getting more and more pervasive and critical. So these programs are also very hard to get right? So there's this previous study done by Shan Lu and her group that shows a lot of real-world multi-threaded code is plagued with concurrency bugs, such as the data races, atomicity violations, which means a set of memory accesses should be atomic, but the code doesn't enforce atomicity, right? And also all the violations, which means one operation must happen before another, but the code doesn't really enforce that, or deadlock, right? Circular wait threads get stuck; they cannot make progress, right? And also our recent work shows that these concurrency bugs can be exploited by attackers, right? So they can launch attacks, just like buffer overruns, right? So these bugs. Let's look at what a concurrency bug is like, right? So this is a real bug in the Apache bug database. This is the bug ID 21287. So this is a simplified version. So two threads, one thread that dereferences shared object obj, another thread refrees this obj. If you execute these two accesses in this particular order, the code would run just fine. However, if you execute code in this particular order, right, so you actually will run into a use after free error. So you may see a crash, or attackers can exploit this memory corruption, right? So this is one of the typical concurrency bugs we see in real-world programs. So let me talk about a few terms. So here we say input to program essentially is all the data a program reads from its environment, which includes maybe the command line arguments or data read from a file, from a socket, or environment variables, right? And we use a schedule to indicate a sequence of communication operations, such as a list of lock operations, for example, right? And also we use a buggy schedule to indicate a schedule that triggers a concurrency bug, just like this schedule, the schedule on your right, right? That schedule is the buggy schedule. So strictly speaking, a concurrency bug can be triggered by a combination of input and schedule, right? But previous study has shown that most of the time the concurrency bugs actually depend on the schedule, not much more than they depend on input. So we'll attribute what triggers the bug by the schedule, right? We say schedule is buggy if it triggers a concurrency bug, right? So what you can view them as synchronization operations or shared memory accesses, right? Right. So how do we actually detect concurrency bugs? How do we find these buggy schedules so that developers can repeat bugs and fix bugs, right? So in the last decade also, we see a lot of advances in making better tools to find bugs, right? So actually came from this system community. Around year 2000, the focus of the systems researchers, right, shifted from performance to reliability, right? The argument there was, hardware is getting faster and faster, but if the code doesn't really give you the correct result, the performance wouldn't be that meaningful, right? So a lot of people started working on building better tools. And also, actually see that a lot of other researchers in the other fields, right, actually start working on reliability problems as well, right, to build better tools. But today we have actually a lot of good tools to use, such as the covariety static analysis tool, which was a spun-off from the Stanford meta-compilation group. I was part of the group during my PhD, right? We also have, the SLAM model checker for, verifying safety of drivers. And also we have like verified compilers and verified operating systems, right? We have lots of great tools today. And one particular direction I worked on, right, is I call this a vulgar version of model checking. So it's not the model checking which I talked about yesterday, where developers write a model of their program in some language, right? Some logical language. Here, we actually use the code as its model, and we systematically try different possible executions of the code to see if we can find a bug, right? For example, recall the Apache bug example I showed you on the earlier slide. We can try to run the code in one schedule, right? One schedule of the code to see if the bug shows up, or we can try another schedule and systematically try different schedules to catch the concurrency errors, right? And this approach actually was pioneered by Patrice Godefroy in his 1997 Popper paper, and then a lot of different folks worked on this technique. So the underlying papers are my work. We worked on making this approach much more lighter weight so that we can apply it to like real large-scale systems. For example, we checked a lot of real-world storage systems such as Linux file systems or the VMware virtual disk implementation. We also checked the distributed systems run by Microsoft data center machines. This approach, right, this vulgar version of model checking worked pretty well in terms of detecting bugs, right? We found lots of serious bugs, such as bugs that can cause you to lose all your file system data, or bugs that can cause Microsoft data center to not make progress, right? These are pretty serious bugs, and developers are willing to fix those bugs, right? But at the same time, when we try to get high coverage, right, when apply these vulgar model checkers to check parallel programs, concurrent programs, we actually run into a lot of issues, right? So concurrency still remains the bane of these tools, right? Still very hard to check. So let me illustrate this difficulty using a contrived program, right? So I have M threads in this program. Each program acquires the same log k times, right? So each thread has k critical sections. So how many schedules will this program have if we repeatedly run the program? Well, the number of schedules is actually exponential in both the number of threads and also the number of critical sections of each thread, right? So let's just look at the, a lower bound of the number of schedules, right? So if you look at the first step done by each thread, there are m critical sections there, and any possible order the threads enters the critical section, right, can lead to some different result. So at least for the first step, there are m factorial number of possible schedules, right? And we have, case steps here, right? So the number, this is actually a lower bound, right? We have at least this many schedules, right? So it's exponential in both the number of threads and also the number of critical sections done by each thread. So this is only a contrived example. It's the schedule of this program is data independent, right? So whatever input you feed to this program, the schedule does not have to change, right? If you think about real-world programs, you aggregate all the schedules for each different input, you can get like a really, really large set of schedules, right? So how do we actually find concurrency bugs or buggy schedules in these programs, right? So, in the general case, you have to systematically try different schedules to see whether or not, there's a bug, right? So essentially, like finding concurrency errors, right? Finding buggy schedules, it's like finding needles in a haystack, right? Like a few buggy schedules out of many possible schedules, right? It's a very hard problem. So how can we actually, improve coverage of checking, right? Like testing or the vulgar version of model checking, right? Make them, cover more possible schedules. So I'm going to show you the traditional way to do that, of doing that using this figure, right? So let's say this is a set of possible schedules my program may run into, at runtime, right? And let's say, this, green circle is the number of schedules that we can check using our limited resource, right? I can systematically try different schedules, right? So the checking coverage will be defined by C divided by R, the number of checked schedules divided by the number of possible schedules, right? So how do we actually improve checking coverage? So traditionally, the approach is we'll make this number of checked schedules bigger, right? Larger, so that we get better coverage. We do so by exploiting equivalence, right? So if there's one schedule, right, it is buggy if and only if another schedule is buggy, then we just need to check this one schedule, and it's equivalent to check the other schedule so that we can put the other schedule also into the, this checked number of schedules, right, into the checked space, right? So this is the traditional approach. But if you look at like real-world programs, right, it's pretty rare to have fully equivalent schedules, right? First of all, and second, if there is equivalence there, it's also very hard to find because these are general programs. They're very hard to analyze, right? So you won't be able to precisely understand what the schedules do, right? Therefore, it's hard to find equivalence. So previously, we worked on a technique we call dynamic interface reduction. So it's actually very similar to the very similar to the compositional model checking technique in the classic model checking literature. The idea is, instead of checking an entire system as a whole, we can split the system into components and check each component in isolation. So by doing divide and conquer, we essentially, find more schedules that are equivalent, right? So this. So partial order reduction talks about basically, a set of independent actions, right? You can check different orders, but here we're actually looking at the operations done at each component, right? You can see it as, if this node sends the same message regardless of how the thread interleaves, right? Therefore, we actually do not have to check the whole thing. We just check this node against the messages, right? And this is actually different from partial order because partial order looks at the entire action sequence. We're only looking at components, right? Okay, good question. So, this works, gives us exponential reduction, but at the same time, it's like really hard to, the algorithms are very hard to come up, right? And also the implementation is like even harder, right? If you want to make it with real-world programs. So this work alone like took a bunch of people, including my brilliant collaborators, right? 3 years to come up, right? So maybe we're not very smart, but if you look at the field, right, like other folks who are working on this type of model checking, and the other technique predates ours, right, the practical ones, right, is this partial order reduction technique Moshe mentioned. It's proposed in this 97 Purple paper, right? So like besides these two techniques, actually there are like no other practical reduction techniques for this type of model checking, right? So finding equivalence is hard. Making C larger is hard, right? So how can we actually increase checking coverage without equivalence, right? So the coverage is defined by the number of checked schedules divided by the total number of schedules, right? How can we improve coverage? You guys can tell me, right? How can we improve coverage here? Make the coverage larger? You make R smaller, right?
So, coverage is defined by C divided bar. If you can shrink the set of possible schedules the program may run into at runtime, like get like automatically improved coverage, right? So that's essentially the idea of stable multithreading, right? We want to shrink the set of possible schedules. So let's look at this program again, M threads, K critical sections. How can we improve coverage? Well, I can run this program with a scheduler which enforces a round-robin scheduling, right, policy. So for each thread, I let the threads do a synchronization and then move on to the next thread, right? And once we reach the last thread, I go to the first thread and repeat, right? So with this simple scheduler, which greatly shrinks the set of schedules we may run into at runtime, right? We can make finding concurrency errors equivalent to finding checking just one schedule, right? If this schedule is correct, it doesn't trigger concurrency bugs, we're done finding concurrency bugs, right? So this approach, right, this stable multithreading idea actually makes finding concurrency bugs and makes checking really simple. It feels like we're cheating, right? So this is very easy to do, right, compared to like finding equivalence. Okay, so the program I just showed you is a simple control program. It's pretty much like data independent, right, the schedule. So what about real-world programs that take inputs, right? So previously we conducted a study on a wide range of programs, including server programs, desktop programs, scientific computation programs, video decoding, lots of different programs. And we actually found out that often the case, right? So if you give me a large range of inputs, right, I can find the equivalent set of schedules that can all process the input, right? Which means I just need to take one schedule out of the equivalent class. I don't really need the whole set of schedules in this equivalent class, right? So this is one observation. So an example I typically gave is this parallel compression utility pervasive, right? So this program takes a file, splits the file into multiple blocks, and then compresses each block in parallel using multiple threads, right? So that's the simple idea. And if you look at the compression schedule of this pervasive tool, right? So once you fix the number of file blocks, and number of threads, you can pretty much use the same compression schedule to compress any file, regardless of file contents, right? So the schedules here are actually not that data independent, right? You just need the same number of file blocks, the same number of threads, right? Then same schedule works for pretty much all files, right? So this means that we can vastly shrink the set of possible schedules, right, without causing issues such as for a file we cannot compress, right. And also second, we measured the overhead of running the same schedule on many different inputs, right. And we found that you may actually think that once we shrink the set of schedules, right, you'll get like a really large overhead, right. But based on some approaches we investigated, right, the overhead is actually reasonable. It's roughly 15%, right? Sometimes less than 15%. That's a reasonable overhead to pay, for the much more improved reliability, right? Worst case is roughly like 4 times, 3.5 times. So here we're talking about overhead on real-world programs. Like if you want to game the system, you can probably come up with like some weird code examples that cause a large overhead, right? But in practice, programs are not written that way, right? Okay, I'll talk more about that later in my talk, right? So this slide shows basically the conceptual idea of stable multithreading, right? So on this first figure on your left, right, we actually depicts traditional multithreading, right, where you have many inputs and you have many schedules, and it's a many-to-many mapping from input schedules, right? When you run these programs, so each input can execute under many different schedules, right? Because the instructions can easily be in many different ways, not determine them, and also many different inputs can be processed by the same schedule, right? Because the schedule corresponds to high-level communication operations, and the schedule is mostly independent of the local data computations, right? And here, the red star represents a buggy schedule, and you see that if you run this program on one input, once, right, you may get a correct schedule, right, which no bug shows up. But if you run it again, you may actually run into the red star, so which complicates a lot of things in multithreading, right? And if you look at this figure, which depicts stable multithreading, essentially we map a large set of inputs, right, all inputs into a much smaller set of schedules, right? So it's a lot simpler, right, this mapping, and a lot easier to get right. If you check these schedules, right, you can get a high coverage because the total set of schedules are small, right? And it benefits not only testing or this vulgar version of model checking I talked about. It can also improve static analysis and possibly verification as well. Because when the set of schedules are small, you can verify much stronger invariance, right? Because you don't want to verify invariance that holds for all possible schedules, right? So another way to look at this approach is we make what you check, what you run, right? We cannot check all possible things, but we make the things you check, the things you run in practice, right? So therefore, we get good coverage. And also, an important additional property we provide here is we call stability, which means robustness against input or code perturbations, right? So for example, when you want to reproduce a concurrency bug, right, you may want to add debug code to observe things, right? So when you add the debug code, because we're going to map similar programs to the same set of schedules, therefore there's a much higher chance that you can reproduce the same bug, right? And also, let's say you observe the concurrency bug on a large file, right? Now you want to reproduce the bug by reproducing the bug on a much smaller file, right? So that you can easily debug it. And when you do that, right, the input, if they do not invalidate the schedule you use, right, will be mapped to the same schedule. Therefore, we can easily reproduce bug as well, right? So essentially, we map similar code, right, and also similar inputs to the same set of schedules, make the program more robust to input and program changes, right? That's what we call stability, and we believe it's very crucial for reliability, right? Because if you think about testing, right, we cannot test all possible input space, for example, right, even in sequential case. And what people do is you test some representative inputs, and hopefully when you run the programs on different inputs, you observe similar behaviors, right? And with stability, you sort of have this nice property, right? Okay, so far I talked about what we believe makes multi-threaded programs hard to get right. They have too many schedules, right? And I talked about this vision, this idea of like shrinking the set of schedules. I'll tell you about implementation later. But an interesting question I'd like to ask you guys is, so far I haven't really mentioned this buzzword of nondeterminism, right? Which means same input, same program, different behaviors. I haven't really mentioned this buzzword. But you often hear people say, look, nondeterminism is the root cause that makes multithreading hard, and if you bring determinism to multithreading, you solve these problems, right? So why is this the case, right? So determinism, this property actually is useful. So I believe it's very useful. But for the purpose of this workshop, right, I like to be controversial. So I just say determinism is neither sufficient or necessary for reliability, right? So the next section of my talk, I'm going to argue for this, right? So how do we bring determinism to multithreading? Previous folks have worked on, including us, right? We have worked on systems we call deterministic multithreading systems. The idea is we force the program to always use the same schedule to process the same input, right? Therefore, if you just run one testing execution on a particular input, right? Let's say I run this program on this input, right? And you test that the schedule doesn't introduce any concurrency errors. And in all future executions, the deterministic multithreading system, the DMT systems, will force the program to always use the same schedule. Therefore, you won't have concurrency bugs, right? The one testing execution.
Just a small question. So when you're on
a schedule means, so you can think of it as, let's say, a total order of synchronization operations, right? So different multi-threading systems, DMT or stable MT systems, define the schedules differently, right? So from a high level, a schedule just means like the communication operations such as shared memory access or synchronization, right? And if you want to get a really concrete idea for one particular type of schedule, think of a total order of synchronization operations, right? The lock operations must be in total order.
Rights to shared memory.
What?
Reads and writes to shared memory.
Reason is right to share memory. If you assume like lock-free program, risk-free programs, right? You can make the synchronization, the same, right? The total order of synchronization operations, right? Always repeat the same order of synchronization operations. You can get a deterministic result, right? If the program is risk-free, right? Because non-determined comes from like threads enter critical sections in different order.
But how many?
So we have actually techniques to make resist deterministic as well. Because different systems define these schedules differently, right? So I can talk with you offline on how we did that, right? Okay. So, DMT basically, you make testing more confident, essentially, or more assuring. And also, let's say you want to reproduce the concurrency error, right? So in the non-deterministic, in the traditional case, right, like reproducing a bug is hard because for this particular bug, we want to reproduce that on one particular input. There may be many possible schedules, so it's hard to hit this buggy schedule again, right? If you attach your program to a debugger, for example, right? But in this case, if there's a bug that's showing up in the field, once I get the exact input, right, I rerun the program with a DMT system, and the DMT system will force the program to use the same bug schedule, so the bug shows up, right? Reproducing a concurrent bug requires only the input, right? The exact input doesn't really require the schedule, right? So a lot of folks have worked on DMT systems. We actually worked on it as well previously, right? So, determinism does have benefits, right? But is this what developer really want, right? So let's look at a deterministic system, but also like the system is very hard to be made reliable, right? Let's recall the same example with M threads and K critical sections. And suppose I have a deterministic system that maps each input, right, to one particular schedule, but for slightly different inputs, right? Each different input, I'm going to use a different schedule to process the input, right? For example, I get input 1, I'm going to use this particular schedule, right? And now I get input 2, I'm going to switch to another schedule, right? And for more inputs, for different inputs, I'm going to use different schedule, right? So if you look at such a deterministic system, right, although it's fully deterministic, same input gives me the same result, right? But if you just change the input slightly, you're going to use different schedules, right? So the result is you still have a lot of schedules to check to find concurrency bugs, right? And also, across similar inputs, right, like the results are very different, right? For example, if you run PVZ2 on one file, it's correct, right? You test the execution there. But if you just change one bit in the input, right, and the DMT system forces the PVZ2, the parallel compression utility, to find a different schedule, which may actually have bugs, right? So this is not really what developers want, right? So determinism, has limitations, and here, this example, right, is very deterministic, fully deterministic, but actually it's not very easy to make the system reliable, right? So there's still a lot of schedules, and also you don't have this nice property stability, right? So the problem here is, determinism is a narrow property, right? So it dictates that the same input plus the same program always gives you the same behavior, right? So that's what determinism says. If you change the input slightly, such as reducing the test case a little bit, right? Or you change the code slightly by adding some debug statements, right? You actually, you're out of the scope of determinism, right? Determinism has no say in that case when the input or program changes slightly, right? Okay. So people often conflate these two different properties, determinism and stability, right? Determinism, same input, same program, same result, right? And stability means like if you perturb things, right, you expect the same behavior, right? These are actually separate properties, but people often conflate those, right? Okay, so determinism and stability, they're not mutually exclusive, right? If you look at this system, right, it maps the whole set of inputs to much reduced set of schedules, right? But it also maps one input to exactly one schedule, right? So it's both stable and deterministic, right? But this is not necessary, which means like a stable multithreading system doesn't have to be deterministic, right? So let me show you, another example, right? If you look at this example, it still maps the same set of inputs to a much reduced set of schedules, but at the same time, some inputs actually map to more than one schedules, right? So if you look at the definition of determinism, it's essentially a binary property, right? So you have some inputs that map to more than one schedules, which may give you two possible outcomes, right? You would say this system is not deterministic, but still, for this program, we can get, for this system in the middle, although it's not deterministic, we can get the really high coverage as well, right, by systematically checking the schedules, right? So non-deterministic but stable doesn't mean that it's hard to be made reliable, right? So, okay, so this shows actually, determinism is not really necessary for reliability, right? I have a question? So here, very interesting in finding concurrency bugs. Like when I say testing, I mean like testing for concurrency errors, right? Which depend much more on the interleaving than on particular input, right? And if you want to check the program for total correctness over all possible inputs, you still need to check all possible inputs, right? That's like a separate problem, right? Instead of like finding concurrency bugs. Okay? All right, so I argued that determinism is not sufficient nor necessary for reliability. What we really want is we want this stability, right? The robustness against input and program changes. I also talked about the.
Why is this
Okay.
Why is it made reliable for checking? Because now
Okay.
You want it again and you don't see the bug, right?
So because
on the same input and now suddenly you don't see the bug, right?
so you're saying like we're sort of hiding the bugs here, right? And you know, I want to say that if you have a bug that you cannot observe, regardless of how you execute the program, right, then the bug is not there. Right?
Maybe one schedule will give you the bug and one schedule won't give you the bug, right?
Okay.
You will run the same program on the same input.
Okay.
And suddenly you don't see the bug.
So you're saying like the concurrency bug depends on the particular input.
Depends on the schedule. No, even for the same input, the
Okay.
bug may show up or not show up because you can have multiple schedules for the same input, right?
Okay, but you know, if I have just like a small set of schedules, I can use tools such as the tools we previously built or the chat tool from MSR, where we can systematically explore the different possible schedules, right? And yeah, okay, good.
And in practice, how small is the small set?
So very good question, right? For PBZ tool, this is my example I often give, right? So it turns out you just need like 2 schedules, right, to cover pretty much all files and the typical setup. So like, you know, the program is not terminated using a signal in the middle of execution, right? If you run the programs without, you know, these abnormal terminations, right? Basically 2 schedules are enough, right? Like it's just, you know, split the files into multiple blocks and then hand the blocks to multiple worker threads, right? Consumer threads will compress the threads in parallel, right? So that schedule doesn't really depend on the file data, right? And that's my example. And for a lot of other programs, like even Apache web server, right? It turns out you don't need like that many schedules to process the request, right? So mostly, you know, you read the files, you know, you send the files to the client, right? If you have multiple clients coming at the same time, you know, let's say, you know, you have 4 clients, right? You have 4 threads running, you just pretty much need a few schedules to serve the 4 clients, right? Next 4 clients come, you use the same schedule, right? That's for Apache, right? For other programs, you know, the schedules are more or less not dependent on the input, right? The data, right? Computation data.
But both of these examples seems to be fairly self-contained threads with little communication.
Okay.
So what about your worst case, something that...
Worst case, you know, worst case can be I have a thread running, and that thread does some synchronization based on the actual data, right? For example, my example with C is pfScan, which is a parallel file wrapper, right? So you can say this is the keyword I want to search, you know, search it in this set of files, and that tool will split the files into groups and search the groups in parallel, right? And whenever it finds a match for the keyword, it's increment the counter by 1, right? And for such a program, right, it's hard to reuse the synchronization schedule because the schedule depends on when the match happens in the file, right? So
It's still a simple example because
okay.
you're hitting one variable.
Okay.
Imagine you actually have many threads operating over most of the memory.
Okay.
Synchronizing, so indirectly.
So, like, why would that? So as long as the synchronization operations, right? If you're just focusing on synchronization operations, I assume the program is free, right? If you just focus on synchronization operations, right? And if the synchronization operations actually do not depend on the concrete value of the memory, right? You can operate on a really, really large set of data and split the data into, you know.
Okay, maybe offline would be best.
Okay. Okay. How about this offline?
So, if you have conditional critical region,
okay.
the synchronization always depends on the memory.
Here I'm talking about control dependency. So it's more like, you know, there's a flag that says whether or not I do this lock operation or not, right? So there's dependency between the synchronization and the flag, right? Of course, you can have other, you know, variables that affect the value of the flag, right? So we track those type of data dependency as well. So actually, you know, let me show you how we implement this, right? So far I just talked about this idea, reducing schedule, right? So let me talk about how we implement that, so maybe your question will become clear then, right? Okay?
So how do you actually, you know, this vision is kind of interesting. You can shrink the set of schedules. You know, what you check becomes what you run, right? So how do we actually do that? How do we implement that, right? There are a set of challenges, right? First of all, we want to map inputs to a very small set of schedules, right? How do we actually compute this set of schedules, right? There's some constraints on the schedules, right? First of all, you know, for every input, I want to at least find a schedule to process that, right? So there's some feasibility issue whether the schedule can process the input, right? And also we want the schedules to be reasonably efficient as well, right? And once we select the a schedule, right, map an input to a schedule, at runtime we want to enforce the program to follow the schedule, right? How can we do that despite of data races, right? So data races may cause executions to diverge from the given schedule, right? And also, how do we make this approach, really simple and deployable so that we can foresee that, folks take over our techniques and run that in their deployed systems, right? And lastly, how can we really quantitatively demonstrate that this approach can benefit the reliability, right? So we see a lot of arguments on paper. Folks say, look, determinism is good, blah, 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 right? But how can we really show that it's good, right? Or stable multithreading can improve things, right? For example, how can we build static analysis frameworks, right, that are very precise, that analyze the program with respect to the small set of schedules instead of all possible schedules? And also, how can we demonstrate that, for this Vargo version model checking, we can get really high coverage, right? So I'll talk about actually probably it's going to be what time? How much time do I have? Okay, I'll be very brief. So let's look at the first challenge. How do we map schedules to input? So first of all, once we map input to a schedule, right? We'll make sure that we can actually process the particular input using the schedule, right? So we need this feasibility requirement. And also, we want to shrink the set of schedules hugely, right? Which means we want to find schedules that can process a large range of inputs, right? And lastly, we want the schedule to be reasonably fast because we want small, low performance overhead, right? So let me illustrate the challenge using two examples, right? First of all, if you look at this example, so let's say lock and unlock is part of my schedule, right? The synchronization schedule, and x is the variable that comes from input, right? So this schedule actually depends on input, right? If x is 0, I cannot really enforce a schedule that contains this lock and unlock operations, right? So we need to capture the schedule and input dependency, right? And also, we need to make sure the schedules are efficient as well. So if you look at this, this example is actually the same mthreads k critical section example. And if I select a schedule that runs the first thread to the end and then run the second thread, right? And so this schedule can be reused on all inputs, right? Because this program is input dependent. But at the same time, you get really bad performance. You basically serialize all the parallel computations, right? So that's not good. So how do we actually solve this problem? So the first approach we came up is we actually use this record and reuse approach, right? So when we see an input we have never seen before, we don't know how to map it to a schedule. We actually run the system's scheduler, the OS scheduler, right, to process the input, because this scheduler most likely will give me interesting, efficient schedule, right, and also feasible schedule as well, right? So once I get this schedule, I'm going to compute the schedule input dependency, right, and also compute that by generating a set of constraints we call precondition of the schedule, right? And in the future, if I see another input that satisfies the precondition, then the precondition is sufficient to enforce, to guarantee that the input can execute on the schedule, right? So that's the basic idea. But this step turns out very hard. Basically, look at the schedule and figure out how it depends on input, right? It's kind of hard. I'm going to illustrate that using, this is the same example. So the schedule depends on, the lock and unlock schedule depends on the input variable x. But here, let's say you have another input variable. There's a conditional depending on the input variable. But regardless of which branch you take, you don't really affect synchronization at all, right? So here, let's concentrate on synchronization schedules, right? So the precondition of the schedule should constrain x but not y, right? So we solve this problem by combining symbolic execution, right? So when we run the program, we keep track of how it observes inputs, right? Constraints on the input. And also once we're done with the execution, we record a schedule, and we can also remove the constraints, right? That do not affect schedules, right? Use precondition slicing. So that's how we solve this problem, and this is our first approach. And the results are reasonable. And also this this technique is so complicated that we actually got an SST paper and OSDI paper out of this technique. But the problem is this technique is still very complicated and it's very hard to deploy, right? If you talk to people, developers who build real-world systems, and they say, look, when you deploy your system, you need to deploy a symbolic execution engine plus a precondition engine together with your system, right? And most likely they'll say no, we don't want to use your technique, right? And so recently we've been working on how to actually make this technique really, really easy to use and deployable, right? Let me actually skip the next point, right? So I just talk about how to make it, practical, right, and easy to use. I actually want to show this slide, but for some reason it doesn't go forward like this.
Concurrency bug.
Probably a sequential bug, right? It's one version of PowerPoint running. How do we?
What do you want to do?
I want forward to this slide. It doesn't really forward.
No.
Okay. I'm gonna go here. Yeah. Keep slides, right?
No, wait.
It's more deterministic, right? Like just one version.
To mirror screen.
Okay, cool. All right, just quickly.
Yep.
So, that's the first try. We need symbolic execution, we need preconditional slicing. It's pretty complicated. Give us 2 papers, right? But we're not, very satisfied with that solution because it's very hard to deploy, right? So how can we actually come up with a technique that people can deploy, right? We reduce the set of schedules and also give them reasonable overhead. Also, like the technique has to be simple so that developers really buy that, right? So first of all, you cannot really ignore performance, right? So the issue here is if you reduce the set of schedules, right? At runtime, the runtime system doesn't have a whole lot of flexibility, right? Therefore, you run into cases where threads have load imbalance in the sense that let's think about this round-robin schedule, right? If one thread quickly finishes the computation and wait to do the next synchronization operation, right? But the thread ahead of this thread, right, in the round-robin scheduling has a really large computation to do and hasn't reached the synchronization yet. So this second thread, right, this thread will be waiting, right, and idly waiting, which doesn't really compute anything, right? That's actually pure overhead, right? And if you ignore load balance, right, you see like thread the balance, the workload of each thread can be hugely imbalanced, right? We actually empirically observed more than 100 times slowdown, pathological slowdown, right, for a prior system called dthreads, right? Because the computations you want to do in parallel, such as compressing file blocks in parallel, right, actually made the run in serial, right? So that's not good. So this record and reuse approach will give you reasonable performance because it will select a schedule the OS scheduler gives us, right, which is reasonably efficient, but it requires like very sophisticated program analysis techniques. Developers don't want to deploy with their production systems, right? And another approach people came up with this instruction counting approach, where we actually count the number of instructions a thread runs, right, as the number of work, the amount of work it does, right? And we can balance threads by, for example, let the thread with the minimal number of executions do the next synchronization, right? So this approach gives you fine-grained load balance, but the problem is it's not stable, which means if you change the input slightly or change the code slightly, right, by adding debug statements, you cause the number of instructions executed by the program, the thread, right, to change. Therefore, you get different schedule, right? So it's not the ideal approach as well, right? Hard to deploy. So it turns out, this seems to be like a very hard problem, and we've been thinking about that for a while, right? Like a few years, and also like folks in the DMT and stable MT field, they've been thinking about it for a few years as well, but we hadn't been able to come up with a good solution, right? Until recently, and turns out there's like a very simple solution, right? So the insight here is, to get a reasonable performance, right? To make the overhead not that large, right? You don't really need fine-grained, load balancing using instruction counting, right? Instead, you just look at the core computations done by each thread and just make these run in parallel, right? And that will give you a very reasonable performance, right? So we build a system leveraging this insight. It's called Parrot. And so by default, this Parrot system enforces a round-robin order for synchronization, right? The first thread enters synchronization first, second thread second, and then repeat, right? So this is the default schedule. If this schedule is fast enough for your program, right, then you're all done. No more work from you, right? But if this schedule gives you bad performance, such as the computations, parallel computations are serialized, Parrot provides a new programming abstraction we call performance hints, right? These are hints just for performance, and developers can add these simple hints to their code for performance, right? And they are different from synchronizations because the runtime system can just totally ignore the hints without introducing any correctness bugs, right? So currently we provide 2 types of hints. One is called the soft soft barrier is for co-scheduling a set of computations, right? In the parallel compression utility pervasive case, you want the file compressed to run in parallel, just insert into your code. So at this point, and this point in my thread, I want they run in parallel, right? So that I get good performance, right? So do that using a soft barrier, insert soft barrier weight in your program, right? And also we have this second abstraction we call performance critical section, which is a chunk of code that the runtime should get through fast, right? Like you should give it the highest priority, or if you're using stable MT or DMT, right? You shouldn't enforce any actual execution constraints, right? All the constraints on this chunk of code, just like finish it fast, right? Because that performance, that's critical, that section is performance critical, right? The section of code, right? So we evaluated on lots of programs, right? And I see that hints are actually pretty easy to add, right? Like doesn't require a whole lot of knowledge and time, right? And also they actually make execution fast. So this is the system I feel the most happy about along this research line. If you guys are interested, you can actually check out our source code, right? It's released on GitHub, right? So so I'll skip this example. So just quickly talk about the evaluation, right? So, so because like this parallel system is so easy to use, right? So easy to deploy, we actually run it on a diverse set of 108 parallel programs. So these include over half real-world programs such as Berkeley DB database, the OpenRP direct access server, Imagine Magic, a suite of image manipulation utilities, and also the aforementioned PPT tool like Redis key value store, right? And also for complete benchmark sets, because previous evaluation, they tend to use hand-picked programs from these benchmarks. Here, we want to use complete benchmark suites so that we can, we do not bias our results, right? And also, use maximum allowed cores. In contrast, previous evaluation typically use just like roughly 8 cores, right? And also, we use like the largest possible workload and our representative workload from real world, right, to measure the performance, right? So this slide actually shows the overhead. You guys don't have to read the program name here, so I'll walk you through the slide, right? So here, this X, right, lists the programs we evaluated, and this X shows the normalized performance. And if it's above 1, means we have some overhead, right? Below 1 means we have some speed up, right? So this is normalized over execution without the parrot, right? Without the parrot system, right? And so here I showed a set of real-world programs, and this is the image magic image manipulation set. And here we also looked at all parallel algorithm implementations in the C++ SCL library. And these are, for widely used parallel benchmarks, right? Complete result for all benchmarks, right? And this line actually shows the geometric mean of all the overhead is roughly 13%, right, across all programs. Actually, for real-world programs, it's actually the overhead is lower. It's around 7% for real-world program, right? For synthetic benchmarks, for some benchmarks, you have like really high overhead, right? This particular one is less than 4 times, right? 3.7, right? So that's the overhead. The overhead is pretty small, and the hints actually reduced the overhead a lot, right? Like from roughly 500% overhead to 13% overhead, right? And also we compared our overhead with 2 prior systems, which also reduced schedules, and we're roughly 10x faster than the prior systems, right? And we also tried, for each program, we tried at least like 3 different workload scales, right? And also very different workload types. And this performance actually results, right, is robust to workload and the type and scale change, right? And also to core count as well, right? And also adding these hints can be like very easy. So on average, you just need 1.2 hints per program, right? And these hints are mostly added by master students working with us, and these students did not have prior research experience, and also didn't write the program themselves, right? But took them roughly less than 2 hours to add these hints, right? I believe the developers of this program would be able to add better hints in less time, right? And so it's pretty easy to use, and it gives you really good performance. And that's actually totally, very simple to use as well, right? Like it's totally deployable. And we looked at the coverage improvement for model checking. We combined it with a model checker called debug, the Vargo version model checker, because it's open source, runs on Linux, and also implement this dynamic partial order reduction. Which is like one of the state-of-the-art reduction techniques, right? And we improved the coverage by orders of magnitude, and also increase the number of verified programs, right, from 33 to 99, right, out of 108, right, for the test setup we used, right. Anyway, so we also build a static analysis framework. You guys can check out our paper from last PRDI, and so this shows some like risk detection results, right? So once you can analyze a multi-threaded program according to a small set of schedules, you can get like very precise risk detection results, right? You can get really few false positives, right? And anyway, just skip those, right? So to conclude, we believe what makes multi-threading hard, right, is not really non-determinism, right? Rather, the root cause is very quantitative, right? There are too many schedules, right? That's hard to check, right? And we came up with this stable multi-threading approach, or stable MT, to vastly shrink the set of schedules, right? By mapping all schedules to just a small set, and we believe this technique can drastically improve reliability, right? For testing, for verification, for static analysis, and you guys can check out our results in these papers, right? That's it. Okay.
Thank you. Any questions?
I'm thinking about problems that are related to data intensity.
Okay.
So today, I mean, access to disk is highly non-deterministic in terms of how long it's going to be able to affect. Even access just to memory, highly non-deterministic, depends on contention.
Okay.
So any problems where the different threads are doing really data access?
Okay. So there are two separate questions here. The first is, if the program is very data intensive, right? And how does this technique work? And the second, there are like these caching factors, like memory caching or disk caching, right? How do we work with this caching factor, right? So for the first question, if the program is very data dependent, right? It doesn't mean the synchronization schedule of the program is very data dependent, right? So think about the compression example again, right? Like once you get a file block, you compress that, right, using whatever compression algorithm.
Because there the compression time is actually very predictable. That's why I'm talking about data access.
Okay.
So to me, data access time is very unpredictable.
Okay.
And so, if the whole point of flexible schedule.
Okay.
That I don't want to slow threads.
Okay.
To slow down the fast threads. Right?
So, for these programs, right, this may have larger overhead, right? But let me give you sorting as an example, right? So think about sorting. If you have one port, right, like people typically use quick sort, right, and you randomly pick a pivot in the middle and split the array into two halves, right? And that may give you like a random repartition, right? So you may get, basically, if you're running in parallel, you get random load balance, right? But actually, if you think about how people do parallel sorting, right, they try to avoid this type of load imbalance, right? Instead, what they do is that there is something called a platonic sort or bitonic sort, right, where you actually predefine the sorting network, right? And they have like 8 levels or several levels, right? So this schedule actually sort of predetermined, right? And the reason they do that is if they have good balance, right, they can get better performance, right, as well, right? Like why don't they just do that, right? And our technique would totally work well with that type of systems, right? So that's the first question, right? The second question is, there can be other system factors that affect timing, such as cache access or disk access, right? And in those scenarios, right, like we may actually want to enforce a particular schedule, but you have to wait in this execution because the data is still in disk read, right? So we do have a performance penalty. But the good thing is, when the program actually go all the way to disk or they receive something from the network, right? And I can roll back to the slide, right? So here you see, like we have the Berkeley DB database, and we use the benchmark the developer use to evaluate their system, right? We have Apache, we have the Redis, which is the key value store powering the Redis website, right? So for these programs, right, you do incur a little bit weight if things are not in cache, right? But the problem is like you go all the way to cache, that's already like a very high overhead, right? So the network latency and also the disk overhead tend to mask the overhead in our system, right? So actually do not see us like having large overhead on those systems, right? Okay. Question?
So I'm curious. So the overhead comes because you have to enforce the schedule.
Right.
And so that means at communication action you will call your scheduler to
right.
do something.
Right. So that's our implementation, right?
And communication actions are monitor acquires, shared memory reads.
So right now we only do the synchronization operations, right? Right, for shared memory access, right? So we have actually another paper I didn't talk about here. It's the SSD11. So the thing is, like, people often say, look, data races make programs not deterministic, so we need to instrument or monitor every shared memory access, right? But actually, that doesn't have to be the case, right? If you think about non-execution, which often only have small regions that contain races, right?
Worst case, you have to instrument volatile reads.
Sure. In the worst case, right? If the program does a whole lot of volatile reads and doesn't do synchronization to protect the reads, right? Then we need to instrument those.
Well, I mean, in Java, typically you use volatile instead of synchronization. So
Okay.
you don't put logs.
Okay.
You know, the typical rate is about 100,000 monitor access per second.
Okay.
And about the same in volatile access.
So this volatile access is protected by logs or
Of
monitors?
course not.
So it's just a volatile. Okay.
You know, that's what the whole point of volatile.
Okay. So you see, for the program we looked at, they use logs most of the time, and they only use like the volatile access occasionally, like as a ad hoc synchronization flag, right?
It's hundreds of thousand times per second.
Okay.
On real benchmarks. Big
Okay. Okay. I'm interested to see how this work with the volatile accesses, right? So maybe there's some technique as well. You know, maybe we can cluster the volatile accesses, right? And you for some order there, right? I think that it's also possible that this would work for Java programs. We haven't tried that yet. Okay.
Okay, so let's take more questions offline.
Okay.
This was mine, but it didn't work.